Now, very interesting things happens if we went into an AC and an AC voltage source and an AC and very interesting things happens when an AC voltage source and a DC voltage source are in series actually. So before, if you don't have a concept of what an AC voltage source is in case of DC voltage source, what happens is that with time the voltage is approximately constant. There is no change in the magnitude. But in case of AC voltage, there is an and there is a fluctuation in magnitude with the change in time, and then this events and this voltage source is characteristic by sign. So I've drawn sign, and this quantity is actually called and the angular frequency or the omega, and it is related to frequency as equal to root 2 pi of f, and this where f is the frequency, and frequency is the number of cycles or number of oscillation per seconds, and usually denoted in hertz. So this is a 10. This 10 denotes the frequency or the angular frequency, and this t is the time. The change in time, this magnitude will change according to the sinusoidal relationship. And 2 voltage, 2 volt is the maximum volt which occurs usually when at 90 degree at 90 degree, when this quantity is equal to 90 radian or 90 in 19 radian 90 degree or pi by 2 in radian, then and this magnitude will be 2. And so when what will happen if we add an AC with a DC voltage, and think simply it will happen that the time axis will be shifted upward by an magnitude equal to the DC voltage is, and this is the DC voltage, and the time axis is shifted here, and the AC voltage will then continue like this. So this is what will happen if an AC and DC are in series. Is now uh, what will happen if an AC A to AC voltages is of different frequencies are in series. So two AC voltages with different frequency. Now one AC voltage is like this, where uh, and another AC voltage with slightly different frequency. We can just draw like this. So when we add these two, we'll have two voltages which are oscillating at different frequencies. So we'll get a we'll get an superposition of these two, and like wave, then there will be two addition of sinusoidal waveform. So the quantity that will come is this across the terminal. Now, another important concept in this is that whatever you do, you cannot connect two voltage sources like this. One voltage sources V1 and another voltage source is connected in parallel. Let this be the case, and this is the case, and if and this is allowed only if this this V1 is equal in magnitude to V2 in case of DC. In case of AC, these two voltages must be at same magnitude, at same frequency, and at same polarity. Also, in case of AC, there cannot be any phase difference between these two voltages. What I meant by phase is that let's suppose that you have an AC voltage like this, and another AC voltage which is not starting at zero but starting with a delay, and these two voltages are oscillating at the same frequency but has a delay, slight delay, and this is the phase between these two. If this is taken as reference, this phase is either usually denoted in degree, and it's called by degree by which this waveform lags this waveform is called the phase. And so these two voltages must also be in at the have equal must be equal in terms of phase. So in case they are connected in parallel. Also, this example showing what can be done, and this is not allowed because 2 and 3 now this voltage is not neither 2 nor 3, and and this should be equal to either of these two, equal to both of these two actually, not either of these two but both of these two, and this is not possible, and so this is not allowed. But again, this is not allowed out because this is allowed. This is not allowed because they are at a different magnitudes, but and this is not allowed because there are different frequencies. So ultimately, the voltage is across the resultant voltage is gets different from either of these two voltages, which is not possible. It has to be equal to both of these voltages. And two current sources can be connected in parallel, however, and they can be added. So if we connect two current sources in parallel, then what will happen is that if we connect two current sources in parallel, then what will happen is that we'll let us see that this is a problem of KCL, Kirchhoff's current law, and what will happen is that this current will be the current flowing through this line would be actually the sum of these two currents, means it will be I1 plus I2. This is I1 and this is I2, then this would be a I1 plus I2. So this is how the current sources in parallel are added. So here's an example showing that and with the different polarities, and the similar approach, and this approach is similar to that in case of a voltage source. Or so DC, and again DC and AC currents can also be added like I showed in case of voltage sources. There is, and also two different two current sources at different frequencies can also be added. Right, but the problem occurs when two current sources in series have the same have different magnitude. Means this is 1 ampere, and here suddenly it cannot be 3 ampere, and so that is not that is not possible, and this is not possible. Similarly, this thing is also not possible, and as in case of AC, in case of AC voltages, is if this is an AC quantity, and this is also an AC quantity. Then these two current sources, when connected in series, must have the same in magnitude, the same phase, and also in the same frequency, so that they can be connected in series. Otherwise, they cannot be connected in series. So with this, I'd like to summarize today's topic, and how voltage source. We've discussed how voltage source in series can be added, how current sources in parallel can be added, and how polarity, magnitude, and also phase affect the connection of voltage and current sources in parallel and series respectively. And also the and also the when the condition is suitable, there can be an equivalent, and source can replace all the other voltage or current sources. So, I would like to conclude this topic with another concept. It is this is called source transformation. This means if it's in solving circuitry problem, we often come across transformation. We often come across various kind of situation in where we might be given voltage sources, and we need we need a current sources to simplify the circuit, it may reduce the problem by may reduce the problem to can make the problem much easier to solve if we transform it into current sources. In some cases, it turns out that we have if we have a current source, then the problem is much easier to solve. That's what I'm trying to tell. So in that case, what is a uh, what is a the procedure to transform a voltage source to a current to an equivalent current source. This is RS, there is the source resistance, and here we can transform it to a current source just by replacing the voltage source with a current whose magnitude is this. Direction is in same as that of the polarity of the voltage source, and in parallel with a resistance RS. Similarly, a transformation of a current source to a voltage source can also be done. And so by multiplying this by the magnitude of the current with the series resistance and connecting in this manner. So this is source transformation, and in next lecture we'll take up Kirchhoff's laws and various network theorems. So goodbye for today. Uh, Thank you.